are people from all over the place, all over the world here. And hopefully we've got some useful information here to share with you. This is a basics of EIS. If you have never done EIS before, this may still be a little intense. We have to expect that you know a little bit about electrochemistry to get going here. But it is to introduce the technique and give you an idea of what it is, how it works, how to look at the data, and some of the things that you can do with it. EIS is a very involved technique. It's very information dense. There's a lot going on in there, and to get a real good understanding of what you're doing with EIS, it takes several courses and a lot of actually working with data and real systems that you'd like to study. That said, I'm going to go ahead and get started. Again, if there are questions, pass them on to Chris. We'll take care of things at the end of the talk. And let's get going. So, impedance. Impedance is a frequency-dependent resistance to current flow of a given circuit element, like a resistor, capacitor, inductance. It assumes an AC current at a given frequency in hertz. The form for impedance is this Z sub omega is the impedance is equal to the frequency-dependent potential over the frequency-dependent current, and this for people that have had electronics in the past looks a lot like Ohm's law because it is. Ohm's law is impedance at the limit of zero frequency. Because impedance assumes an AC current, people will sometimes say things like AC impedance. That's actually a little bit redundant. Impedance is always an AC value. So why do you want to run it? It's theoretically complex. It's more expensive than other even electrochemical techniques. So why bother? And the reason is that the information content of EIS is a lot higher than most DC techniques. There are other advantages to this. One, if you've got two or more different electrochemical reactions taking place, EIS is sometimes able to distinguish between them, disentangle those different processes. It's possible to identify diffusion-limited reactions, like diffusion through a passive film. And EIS can provide some information on the capacitive behavior of the system. And the capacitive information is always somewhat useful. It's particularly useful for systems like coatings. The way the measurement is made, a small sinusoidal perturbation of either potential or current at a single frequency is applied to a cell. The response, which is going to be current or potential, is measured, and the impedance is then computed at each individual frequency. This is repeated for multiple frequencies, and the data is plotted and analyzed. This is what a single frequency excitation and response in EIS looks like in the time domain. So we've got an applied signal. In this case, we're applying a voltage signal at I mean, this is dimensionless. We don't know exactly what frequency, but at some frequency. And we have a measured current response here. So the measured current has a couple different, there is a magnitude associated with both of these. And there is a phase shift. The measured response is not often completely in phase with the original applied signal. So that's one frequency. But an EIS spectra is an entire collection of frequencies. And those frequencies are, oh, I apologize. Hold on just a second. I don't think you guys can hear this, but I can. I hope you guys couldn't hear that. So across a wide variety of a wide range of frequencies, so that data needs to be plotted. So looking at a bunch of individual sine waves just doesn't work. So the way we look at a full EIS spectrum is for that data to be displayed as either a vector or a complex quantity. The vector quantity is defined by the impedance magnitude and the phase angle. And the complex quantity has the total impedance separated and broken down into a real and an imaginary component to that impedance. These vector or complex quantities are different representations, but they are mathematically equivalent. And the way to think about this is if we take a point in space, we can define where that point is in a couple different ways. In the vector quantity, we say we go up a given phase angle from our axis, and then we go a given magnitude or total distance from the origin to where that point is. The complex planes, we just go over on one axis, a given amount, the real axis in this case for impedance, and then we come up on the other axis, which we term the imaginary impedance, to find that exact same point in space. So both of these are just different representations of the same thing. What they look like in terms of an actual EIS spectrum is shown here. This is EIS data, and the two terms that get used. Bode plot is showing the vector quantities. So we have a phase, which drops down, comes back up here in the black, and the modulus or impedance magnitude, which is in the blue, sigmoid. The Nyquist plot is the complex plane plot. So we've got a real impedance and an and technically this is a negative imaginary impedance. And so we're seeing the exact same data plotted in two different ways here. Which one do you want to look at? That is in part a question for you. There are advantages and disadvantages to both. Both the Bode and Nyquist allow you to resolve individual charge transfer processes. Bode has a slight advantage in that frequency is explicit. If you want to know exactly what frequency something is at, you can see it on the Bode plot. It is not obvious on the Nyquist plot. The Bode plot is also plotted with log magnitude and frequency. And so if you've got a very large dynamic range in your impedance, the Bode plot makes it a little bit easier to see what's happening at the low impedance range, even if you have very large impedances. The Nyquist plot, small impedances can be swamped out because it is linear. Frequency is not obvious. That said, this first one, a lot of times things are easier to resolve in the Nyquist plot than they are in the Bode, where they tend to blend together. Individual processes tend to blend together a little bit more. So it's often easier to resolve multiple processes in the Nyquist plot. So that was how the data is collected, how it gets presented, and now briefly we're going to talk about how we actually analyze the data that you see in EIS, and that is through modeling. So we model our data. So the electrochemical itself is going to be substituted for a network of these passive electrical circuit elements, and the network that we build is called an equivalent circuit. The EIS response to that equivalent circuit can be calculated and compared to the actual data that we get, and so you can fit one to real data. The different types of the primary types of circuit elements that we have are resistor, capacitor, and inductor. These are real circuit elements. You can actually find resistors, capacitors, inductance, and build a physical circuit and measure that circuit itself. Resistors have an impedance equal to their resistance. They have no phase shift. That means that the impedance of a resistor is on that real and imaginary scale, it is entirely on the real side. Capacitors and inductors both have 90-degree phase shift. Capacitor is -90 and an inductor is +90 degrees. And their impedance is is frequency dependent. So a capacitor, the impedance of a capacitor is -J over omega C. Omega is this the frequency represented in radians. C is the capacitance. The J is -1. People that have did all of their imaginary math in mathematics classes may remember that as being I. Electrochemists like to use I for current, so J gets used for the square root of -1. And an inductor also has that J terminology in there, and it's directly proportional. So for a capacitor, it's because it's 1 over omega C, or J over omega C, the impedance of a capacitor gets larger with low frequencies, whereas for an inductor, it's directly proportional. As the frequency gets higher, the impedance of an inductor increases. And this J is what makes the term quote unquote imaginary. So the imaginary component has this square root of -1 in it, and that's all that means. And it is still an actual impedance. It just mathematically it has that square root of -1 in it to make it so-called imaginary. So back to our single sign, single frequency time domain plot. This is what the EIS of a resistor would be. The phase shift for a resistor is 0 degrees, so they are in phase with each other. And you've got our applied voltage, measured current. They have magnitudes associated with them, and the ratio of those is going to be the resistance value for that resistor. For a capacitor, we have a 90-degree phase shift between the applied signal and the measured response. But and that's, again, just taking a look at what that is. So those are the elements. What does that mean for electrochemistry? So that's the physics. That's what these different elements are doing. But what's actually happening in the cell? And so what we have here is a model of the double layer. This gray bar is the electrode material itself. These blue dots represent electrons, holes in the surface. We have a layer of solvent sitting directly on top of the electrode surface, and some distance further away we have solvated ions. Maybe we have some other species out in solution that can undergo electron transfer itself. And then over here we have, we're making this measurement. We need a complete circuit, so we have a point where we're measuring the voltage against this surface, or the reference electrode. So this first part is the double layer capacitance. This is a charged plate. Here's a dielectric, which is a solvent dielectric, and here's a row of ions on the outside here. That is a capacitor. It's actually a very large proportional capacitor because this area distance tends to be very small for most electrochemical cells. But this is the double layer. We also have electron transfer resistance. So the moving an electron on or off the electrode itself, whether it's to something out in solution, or if we're reducing, oxidizing the actual material of the surface of the electrode, that model's like a resistor. And finally, in order for all of this current to get through, in order for us to sense the voltage, we're not sensing the voltage right at this point. We're some distance further away. And so as the current flows through the electrolyte we have, there's an uncompensated electrolyte resistance. These elements come together to form a simplified Randall cell. The simplified Randall cell is kind of like the basic unit for EIS. All systems have this. Whether or not you're going to be able to see all of these things is a question, and whether or not there's more involved in your system is also very possible. But this is the basic unit. This is a simplified version because it does not include diffusion, which is the actual Randall cell. If going back, it includes a diffusion element, a Warburg diffusion, which we'll get back to in a little bit. But first, let's take a look at this and see what that looks like. So this is the Bode plot we saw before. Now we actually have a model that describes this Bode plot, and we can take a look at how this response is at different frequencies. So this is log frequency down here. So at very high frequencies, this capacitor has effectively no impedance. So all of the current that flows through at high frequencies is going to go across the capacitor, which has no impedance, and across RU. And none of it is going to go across this RP down here, polarization resistance. So at high frequencies, all we see is RU on the magnitude, and our phase shift is back up at 0. As we go to lower and lower frequencies, this capacitor starts having a meaningful contribution to the impedance. And so we see that in two different ways. First, the total modulus, the total impedance of the cell starts to go up. And because it is increasing due to impedance from a capacitor, the phase angle starts to deflect away from 0 and towards 90. And that represents the current now flowing across an impedance here. But this resistance, the impedance of this resistor down here is not changing as we change our frequency. So as we go to higher and higher frequency, at some point, this double layer capacitor has greater impedance than the polarization resistor we have down here. So most to all of the current starts dividing and going across to RP. So when we get down to very low frequencies, all of the current is going to be coming in. None of it goes across the capacitor, which is effectively an open lead at very low frequencies. And all of the current flows across RP and then RU, which is what we see as the phase gets back up towards 0, that means less and less of the current is flowing across the capacitor, less impedance is reflected by capacitive impedance in the cell. And at very low frequencies, we're back at 0 on the phase, and all of the impedance we see is just the total of RP and RU. This same data shown on the complex plane or Nyquist plot this is a single semicircle, reflects the same way. One of the things that kind of can be confusing at first, if you haven't looked at these before, is high frequency is on the left side of this plot, low frequency is on the right. So at the high frequency limit, we are down here. We're at 0 on the imaginary, and all of the impedance we're measuring is real, and it's equal to RU only. As we go through lower and lower frequencies, we start to see the capacitance pushes this up into the imaginary, negative imaginary direction, until we get to low enough frequencies where all of the current again is flowing through the two resistors only. We're back to 0 on the imaginary, and our real impedance is the sum of RU and RP. So if we take that data and that model, that simplified Randall cell, we can take it, we can fit the data. So this is the model used, the simplified Randalls, and then if we fit the model data to the experimental data, we can pull out values here. So in this case, RP, which is the diameter of this semicircle, is 3 kiloohms. The uncompensated resistance is about 200 ohms, and the double layer capacitance is right about a microfarad. Okay, so those are actual circuit elements that you can go and get and build your own circuit. Electrochemistry's got more going on than that, and the two most noteworthy modeling elements that we need to deal with are Warburg impedance and a constant phase element. The Warburg impedance element is a general impedance circuit element that represents resistance to mass transfer. So this is our diffusion control. This is going to exhibit a 45-degree phase shift. There are multiple varieties of a Warburg. You can have an open-ended. That means that it can do, on the time scale of the experiment, anything that leaves the electrode can diffuse uninhibited as far as away from the electrode as the time allows. Bounded version of this means that diffusion, it's like a hard wall on the other side. It can diffuse so far, but then it encounters something else that bounds the diffusion at a certain point. And then a porous bound. This means that there is some, it can diffuse a certain distance away, at which point there is some form of transition where either usually the mass transport increases dramatically. So either a gel on the surface of the electrode or a rotated disc electrode that gives you a replenished film at a certain distance away. The other element, and the one that actually gets used the most of these two, is the constant phase element. Constant phase element is a very general element. It can technically be used for everything, but in practice, experimentally, we kind of confine its use to control for imperfect capacitors. So CPEs they have a constant phase. That constant phase is usually between, this says 80 to 90. For a lot of cells, you'll actually see phase shifts that are more in the 70 to 80 range, sometimes even lower with certain types of electrodes. But the reason this gets used is because real systems are not perfect. And so a true capacitor assumes completely planar, infinite surface. Real electrodes have some roughness to them, and they have edges on them, and they may have other geometric features. They can have hot and cold zones if you're talking about something where you can get an oxide film or a barrier that is in different areas of the electrode. So the electrode surface itself is rarely completely planar or completely uniform in terms of its activity. And so how that gets reflected is in terms of this adjustment to the capacitance of the electrode, and a constant phase element gets used in that place. What do these look like? This is what a mass transfer looks like, how it affects your EIS spectra. So that initial semicircle that we saw, or on the Bode plot, the sigmoid with the dip, starts out okay, but then at low frequencies, instead of coming back to the axis, it turns around and it just goes off at a straight line here, this 45-degree angle. On the Bode plot, we see instead of plateauing here, it starts to trend back up, and the phase, instead of coming all the way back up to zero, turns around and tends to 45 degrees. This is taken to very low frequencies for a model system. You usually do not get quite to this level with most real systems. But that's what diffusion, unbounded diffusion looks like in on a EIS spectrum. The complex systems may require complex models. So when you're doing modeling for an EIS system, it's important that every element that you have in the equivalent circuit corresponds to some specific activity within your electrochemical cell. This is it. You can always get a better fit in terms of lining up on top of your data by adding more elements and adding more degrees of freedom to the elements that are in there, and you will get better and better fit. But if those added elements don't correspond to something that you understand and know why that's happening, you're going to end up, that's not a good way to do the modeling. So you want to use the simplest model that fits the data. There is a corollary to this, that a lot of times you know that you have complex activity that does not get reflected in the actual EIS spectrum. And so you can't effectively model that complex activity. You have to you really want to use the simplest spectra that fits, the simplest model that fits your data. Unless and until you get more information that allows you to isolate some of those things. But when you're looking at a EIS spectrum, EIS impedance in general requires a handful of things here. It requires that the system that you're measuring be linear, stable, causal. Linear means the system obeys Ohm's law. that the value of the impedance is independent of the magnitude of our perturbation. In a linear system, we don't see any harmonics. Basically, the signal that we apply and the response that we get back are both at the exact same frequency with no additional frequencies on top of them. Stable means that the system does not change within the time frame of the experiment, and that after the perturbation has been removed, it goes back to its original state. The last one is causal. Causal means that the response that we're getting is only due to the perturbation that we're applying, that there's no other processes or things that are happening that are affecting the response that we're seeing. Electrochemistry is not linear, but circuit theory is simplified and actually requires the system to be linear. So the impedance in a linear system is independent of the excitation amplitude. The response of a linear system is at the same frequency as the excitation frequency. But electrochemistry is not linear. And the way that we get around this is we shrink down the voltage window that we look at until this curve looks like a line. So if we look at a small enough region and we keep our signal amplitude confined to that, then our response is within that linear region. If the excitation gets too big, then you start to generate harmonics with that signal, and the EIS modeling doesn't work. The data is not valid. There are ways to make use of the nonlinear region. There are some different techniques. Electrochemical frequency modulation is one of them. Not going to talk about that today, but other than to say there are reasons to make use of it, but EIS itself does not. So the first thing was linear, the next was stable. In order to have valid EIS data, we need to have a stable system. Electrochemistry is not necessarily stable, particularly things like corrosion and batteries, where a little bit of current flowing through the cell can move you into a different region, or time or buildup of films or SEIs or all sorts of things, changes on the electrode surface can change where you are. And so there is a trade-off to be had here. The more stable a system is, the longer you can run. So what the system needs to be is stable over the course of the EIS experiment. So basically, at the start of the experiment and at the end of your EIS experiment, your system needs to have been stable over that time frame. Systems that are very unstable, you're not going to be able to run EIS for as long. It's going to drift. You're going to have background changes. And you're just not going to be able to run to as low a frequency. A good way to check is to use open circuit potential. You can do an open circuit at the beginning, at the end of an experiment, and if those two are the same value or within a couple millivolts, you've got a high degree of confidence that the system was stable over the time course of the experiment. There is another way to take a look at data if you're really not sure what maybe happened, and that's the Kramers-Kronig. Kramers-Kronig transform, or KK transform, is a mathematical evaluation that says that the phase and a magnitude in a real system are related. We apply it's one of the functions within eChem Analyst. You can apply that to the data. And what it is going to do is going to calculate the magnitude from the phase. And if they match the experimental data, you get some confidence in the data. Converse is also true. If they do not match, there's a very high probability that the system is not linear, stable, or causal. One of those things has gone out. Don't necessarily know which one, but something didn't match up. The KK transform does not, however, validate your data. And the reason for that is there are some artifacts that will KK transform as completely valid. The easiest one to talk about is on the instrumentation side, you have a cell cable that goes from the potentiostat to your cell. That cell cable is wires with coaxial things and leads at the end of them. It has a capacitance. If you are measuring capacitors that are very, very small, that cable capacitance can be a significant contributor to your impedance. But a capacitor is a valid circuit element. So if you do a KK transform and you've got instrumentation artifacts from the cell cable, for example, that are dominating your impedance, the KK transform is going to look perfectly good. So, but to kind of give a look at how it might fail, here's a data that looks bad, but we're not necessarily sure how bad. So it looks like this starts out and comes up here, and then things really go bad when it loops around down under here, which is what it's doing on this side. This data here is clearly bad, and so we want to be able to isolate where the end of the good data is and the beginning of the bad data. So you run a KK transform, and something kind of surprising shows up. It shows that all of this data here that looked good is also bad. And so this is where doing a KK transform can be a helpful, even when you have some experience with EIS and you have some familiarity with the spectra, because a lot of this data here that looked at first glance to be good isn't. It's already failed linearity here. Probably the signal was too large. And it was nonlinear. Drift can also be the cause for things like this. So this is a good way to test. I should note, if you take a look on the Bode plot, it's where it starts to pull away from the phase here is where it's starting to go bad. So that's at these frequencies down here, it's already pulled away. It's usually more obvious on both the Nyquist and on the phase component of the Bode than it is on the magnitude for the Bode. So when you're doing analysis, the first thing to do with EIS is to look at the data. As you run more and more of these, especially if you're running similar type systems, there should be an expectation of what the data is going to look like. And if it's starting to deviate from that, then that is a problem. If you're not sure, or if this is your first time running EIS and you don't know whether or not this is what your data is supposed to look like, you can always run a KK transform, and that's a good first step if you don't know. It's also one of the things that oftentimes, if somebody is having trouble modeling data and they contact us and ask, it's like, what's going on? I can't figure out how to fit this. And one of the first things we do is run a KK. If the Kramers-Kronig transform does not line up on top of your data, there is not a model you can build that is going to fit it. It's just not possible. So whether or not you've run Kramers-Kronig, if you're looking at the data, you can determine the number of RC loops. Back on those early Bode Nyquist plots, we had one RC in there from that simplified Randall cell. We had one semicircle. If you have two RCs in there, you should have two semicircles. And so you can determine that number. Usually don't see more than 2 or 3 time constants in a given cell. Lithium-ion batteries are kind of an exception and kind of a mess. But aside from that, you can also determine whether or not you have any inductance. Inductance is more commonly seen in low impedance systems like fuel cells, batteries. Or if there's any diffusion. So Warburg is for diffusion. If there is diffusion, you can take a look and determine boundary conditions. And this is getting into the more advanced type of analysis techniques. So back off from that from now. From that point, you pick and design a model, you fit it, check to see if you need CPEs, transmission lines, another complex element. I will say in almost all real systems, you will need to substitute a constant phase element for your capacitor, for your double layer capacitance, for your coating capacitance. Any capacitance that you have in there is probably going to need to be substituted for a CPE. And then this is an iterative process. You fit, you see how things look, and repeat if you need to. And in the end, you can extract data, resistance values, capacitance of the cell, things like that. So that was kind of how the EIS works in terms of the electrochemistry and how it applies to your cell and what you're actually going to do. But, and I started to note this with the Kramers-Kronig Transform, instrumentation is actually relevant when you take an EIS measurement. For a lot of DC electrochemistry techniques, the instrument is, it is present, it determines some of your limits, but it is not as large a factor in the response that you're seeing as it can be with EIS. So what type of instrumentation goes into making an EIS measurement? The first is a sine wave generator. All of these are AC measurements. It's a sine wave, so we need to have some way to generate a sine wave. And we need to have some way to synchronize the timing such that the applied signal and the measured response, that we know that their phases are aligned or not aligned and what that degree of separation is. And then, because this is electrochemistry, we need a potentiostat galvanostat. Impedance as a general term is something that is broadly applied. If you're, the electronics industry does a lot of impedance analysis. If you're a semiconductor industry, things like that, they're not doing electrochemical impedance. So they do not have potentiostatic control. They're just driving a signal at the end. There's no feedback on that, and they're assuming that the signal gets through and that they're modeling everything there. Electrochemistry is more involved. We use a 3-electrode cell for most electrochemical experiments, and so these traditional, electronics type impedance analyzers are not going to get there. We also have feedback control. So when we apply a signal, we don't just assume that that gets there, because there's ways that that signal can get interrupted. There's bandwidth issues. So we actually measure the signal, even the signal that we're applying, as well as the response, to make sure that if we're asking for 10 millivolts RMS, that we're actually getting to 10 millivolts RMS. And that requires a potentiostat. All of these are, of course, all clumped together into a single instrument. It's gotten, it used to be that these were all separate pieces of instrumentation that had to be used. Now it's relatively easy to actually run an EIS measurement. Still, there are things to be aware of. There's differences between software in terms of setup. There are accuracy and performance limitations of the systems. So, how does the potentiostat actually make this measurement? So, this virtual grad student is the way that Gamry does it internally. There's a class read Z, and what we do is, from a valid impedance measurement, for the initial value, that could be an initial guess at the impedance. Otherwise, it's the previously measured good impedance value. We take that measurement and estimate the impedance, the current response, the noise gain, all the different settings within the potentiostat that we're going to need to make a good measurement at the next frequency. And then we cycle through all of these. Was our AC voltage off? We can adjust the gain. Was our AC current too big or small? Was it outside of the range? We may need to change the estimate or change the IE range that we're in. If we've got too much DC current, we might need to make adjustments, and go through all of the different settings within the system. And this happens fairly quickly. The initial data point that you take takes the longest if the guess is off by a long ways, but eventually, once it goes, it usually, from step to step, everything is very fast. If it keeps adjusting things and cannot take a good impedance measurement, it's going to kick out and it'll report that it's unable to measure. This can happen with systems that are drifting very rapidly, or if the signal that's been applied is too large. That's more common for galvanostatic EIS. So if you get that, there's probably something that needs to be adjusted in the settings and retried, but most of the time everything gets through and it moves on to the next frequency, and it repeats this process. So that's how it works internally. What does it mean to you? One of the things that is a good idea is to check your own potentiostat, whether you're using ours or something else. Understanding where the system limits are, where the potentiostat limits are versus the systems that you're measuring is important. It's also useful if you want to compare different systems, especially if you're looking at a paper where somebody has made the given measurement, you're getting different measurements. It's a good idea to understand whether or not they're actually, that those original measurements and your measurements are really of the same thing, or if you're testing different electrochemical, whether you're testing different systems or whether you're testing electrochemical cell systems, or whether you're testing different cabling, which is not what you want to be doing. Manufacturers do have specifications. I'll take a look at ours, the way that we talk about things in a minute. The problem, of course, is that they are not standardized. And they don't really tell the whole story. Impedance is a dynamic measurement, takes place over a broad, a lot of ranges, and understanding, I mean, just looking at specifications aren't going to necessarily tell you which system is going to be better at impedance. The last thing here is that when you're doing EIS, your setup matters. I talk about the cable regularly because for both very high impedance systems like barrier coatings and for very low impedance systems like batteries and fuel cells, how your cell cable is connected can influence the results that you see. So, what to look at in terms of Spectra? We publish accuracy contour plots. An accuracy contour plot shows the total system performance. For us, all of these signals are valid EIS signals. That is to say, they are less than 10 millivolts. You can make this range look a lot, you can make the accuracy range look better by using a larger signal. But electrochemistry, if you use a larger signal, you get invalid data. So what you really want to know is how good a quality measurement can you get with an electrochemically valid signal. The other thing is that these collecting this takes a long time. There is a shortcut to this. They are open and shorted lead. These are not the same thing as the accuracy contour plot, but I will show you what they are and how to run them if you're interested shortly. EIS Quick Check. So this is what we run. We determine this. This is kind of cumbersome. What you would rather do for yourself if you're trying to do these comparisons is do this EIS Quick Check. And that's just a simple test. It works across different systems, different platforms, however you have your setup, and it gives you a rough idea of what your system performance is. It also helps to establish proper setup for making accurate measurements. And so here's the way that you want to do it. You basically want to run EIS on a few precision resistors. So the examples given here, 100 ohms, a kilo ohm, and 10 kilo ohms. This is going to show you the real system response. So if you have these, and 1% resistors are fine. You don't need traceable 0.01% value resistors for this type of testing. You run it using a potentiostatic signal, 10 millivolts AC, and see what the response you get. A couple other things that you can do, particularly if you are looking at very low impedance systems like batteries and fuel cells and supercapacitors, you may want to run a shorted lead EIS test. This is a galvanostatic test with a fairly large amplitude current AC signal. And this is going to give you an idea of the low impedance limitations of the system. It also gives you a measure of the cable inductance, which can dominate higher frequency, mid to high frequency ranges for low impedance systems. The last one, this is a little bit more optional, is to run an open lead EIS spectra. This becomes more useful if you're doing barrier coatings. Coatings are very high impedance, very small capacitance, and an open lead test is going to give you an idea of where your limits are there and whether you're pushing up against them. Similar to a shorted lead in that we are not using any type of resistors, but we're doing this with a potentiostatic signal. A little bit larger than normal because when you're measuring both open leads and things like barrier coatings, a little bit more signal. You're not doing any actual electrochemistry. You're measuring a capacitance effectively. And this is going to give you a measure of the cable capacitance and show you where the system limit is up there. This is not necessarily useful for accuracy. So cable setup. They said it matters, and here's what it kind of looks like. For some impedance measurements, the cable positioning makes a big difference. So 1 kiloohm is kind of right in the wheelhouse of almost any system, and so it generally does not matter how you make that measurement. For low impedance samples, and for a system that goes up to a megahertz, 100 ohms is actually a relatively low impedance. And for the shorted lead, you want to actually minimize the inductance by twisting cables current pair together from one side and the other. There are some diagrams of this in our application notes that kind of show a little bit better how to do that. These top 2 images are showing the sense. So basically, we've got the blue and white over here are sense leads. So these are the ones that are measuring the voltage. The green and the red are our current carrying leads. They make separate contacts. This is a 4-terminal measurement, which you need to do for low impedance. And we bring the sense in from one side, the current carrying leads in from the other side to minimize inductive pickup. We do the same thing with shorted lead. Our shorted lead in this case is a copper braid. Come back to this. For high impedance, on the other hand, inductance is not your limiting factor. Cable capacitance is. So for the 10 kiloohm, and for an open lead, you want to minimize the cable capacitance. And the way to do that looks similar at first glance, but it's actually kind of the opposite here. So instead of separating the current leads and the sense leads, we pair. So there is a current and a sense lead on each side now, but they are separated from each other as much as possible. And the alligator clips are pointing in. Alligator clips are exposed metal. If you run them parallel, you add capacitance to your measurement. If you are measuring, if you want to measure something that's 100 picofarads, that added capacitance is significant. If you're measuring things that are mostly 10 to 100 ohms at high frequencies and kiloohms, 100 kiloohms up to mega ohm at low frequencies, it probably doesn't matter a whole lot. And a lot of times you end up being constrained by your electrochemical cell anyway. But in terms of absolutely minimizing the cable capacitance for this measurement, this is how you would set that up. One other side note. For the open lead, you actually don't have anything here, but you still short these together, the current and sense on each side. The work and work sense, blue and green, would go inside of a Faraday cage. Counter and reference would stay outside the Faraday cage, actually. So what is a system response for good, just measuring resistors? What you're seeing here is the actual impedance are in the circles, and then the phase are the little pluses here. And what you want to see is that the resistor value is reflected in the impedance magnitude that you're seeing here, and you want a phase of 0 degrees all the way out. So you can see we start to get it deflect a little bit, maybe up to a couple degrees here, but not a whole lot. So magnitude within 1%, phase within 2 degrees. That cable positioning can make a big difference. So 2 degrees worth of phase is perfectly fine. If it's anytime you see things that are talking about like 0.3 degrees, you need to have a lot better control over the system layout and controls to actually determine that. Standard cell cables aren't going to let you get there. In terms of the phase deflections here, if it deflects down into the negative, that it would be a capacitive deflection. If it's deflecting up, it's an inductive deflection. So those were good. What does a bad one really look like? And here's an example. This is a different system. entirely to make this test. And so what you see is at lower frequencies, it's fine. But by the time, once you get past about 40 kilohertz here, 40 to 50 kilohertz, this phase is starting to drift on you and you see a lot more noise. And by the time you get up to a megahertz, it's terrible. So this is a bad response. So if you're ever tried to measure something with this system out here, you're not going to get it. So those are the resistor responses. The shorted lead curve is a little bit different. So shorted lead, we're going to try and short all the leads together. So we have an impedance that is as close to 0 as we can get it and measure what the response is. So what we should see is a very small resistor with inductance at high frequency. So this is the inductive region. So as we get to higher and higher frequencies, the phase starts deflecting positive, the impedance starts increasing. And the reason for this is just from the inductance of the cell cable itself. As you get to high frequencies, you become inductance limiting. If you look over on this axis in terms of what our impedance magnitudes are, here's 1 milliohm. This is 100 microohms. We're down at about 30 microohms here. So these are very, very, very low impedances. Most even relatively, modest size, standard size lithium-ion batteries, you don't usually see much below a milliohm. So this is much lower than you'd likely see for most systems. Another note here, this 30 milliohms down here corresponds roughly to the impedance of a copper braid. So this isn't system limited still. There's a better test that we do internally to actually get at that system limit. The open lead curve is, again, kind of like the opposite of the shorted lead curve. We isolate. So the working and the working sense lead are connected together, and they're inside of a Faraday cage, and then the counter and reference are connected together outside of the Faraday cage. What this should look like is a capacitor, because that's what it is. We've got a big open lead at the end, so the only thing that we're measuring in this system is cable capacitance, and it's residual cable capacitance at that. And so the data should look like a capacitor. That means we need about 90 degrees phase, and if you take a look at the data here, we're at about 90 degrees in terms of phase. And this line on the magnitude is exactly what you expect. Now this is very noisy because this is absolute at the system limit in terms of limited detection. When you try and put a teraohm signal across, a teraohm across 50 millivolts is less than a picoamp. So we're tiny currents down here. And so even inside of a Faraday cage, this is a really good response in terms of what magnitude this is. You're looking, I think this one's in the femtofarad range, about 15 or so, maybe 40 femtofarads, which puts the system limit in terms of what you can measure into the picofarad range. This system does not have low frequency roll-off, but for systems that do not have very low current ranges that are limited to, in the nanoamp or microamp region, you may see this roll off at lower frequencies. Right. So the take home from that quick check is that all impedance systems are going to have limits. The setup matters, and you need to know where your system lies. So if you're doing coatings, you've got high impedance. If you're doing energy devices, batteries, and fuel cells, you're at low impedance. Corrosion can be all over the place. Some corrosion samples are incredibly high impedance. They're basically oxide film coatings that are at the same type of high impedance as barrier coatings. Other corrosions are very large. They're in sulfuric acid, larger sample sizes, and they can be less than an ohm worth of corrosion resistance. Sensors are another one that have a tendency to be all over the place in terms of the impedance. They tend to be more higher than lower, and a lot of times sensors are looking at changes in the capacitance of a system. So that's this kind of take home for what that is. EIS is a versatile technique. It's non-destructive, it's high information content. Running EIS is very easy. Sometimes it's too easy because it gives a false sense of security about what the quality of the data that you're getting back is. EIS modeling analysis is very powerful, but a few things to note. Use the simplest working model. This is going to generally be the best until you have more information that you can put into something. Complex system analysis, however, is very possible, and user expertise can be quite helpful. And with that, here's a list of references. I am not really seeing what time it is. Yeah, we're right at about the hour. This again was this was a basics of EIS. We're looking at understanding the technique, how it applies. The number of systems that it can apply to is any electrochemical system, and there is some valid and valuable data that you can get back from anything. That said, just understanding the technique is a process. It takes a little bit more to understand what you're doing with EIS than it does to understand polarization resistance. It's similar to actually understanding cyclic voltammetry in terms of the amount of information that you're getting out of it, for people familiar with that. And I think Chris said earlier at the beginning that we're hoping that to maybe take this forward so that we can give you a little bit more specific, defined ideas about what to do with this. But for this talk, this introduction, that is what EIS is. That is how it is used. And that is a little bit about what the systems that you're using to make that measurement and how they affect and how you need to understand that to get really the best data out of your EIS spectra and your systems. So with that, I'm going to go ahead and hit the stop share up here. And
okay. Jacob, you were still there, correct?
I should be.
Yes. Okay. And maybe we've had a bunch of questions here that I'd like to pose to you. It might be useful to share your screen once more, and also say at this time, if people would like to raise their hands after we get through the first couple of questions here, and we'll also we can unmute you, and then you could ask your question at that time too. So the first question that we had was, why is the double layer capacitance not shown at high frequency and low frequency? So why do we see RU essentially only at high frequency and RU plus polarization resistance, or RP, at the low frequency?
Okay. Yeah, I'm going to share the screen. That guy, I'll take it off presentation mode. There we go. So at high frequencies, what happens is it's just an electronics behavior. It's so electrons are going to take the path of least resistance every time they come to a junction, and they have to decide. So if they get to this point, the current, when it gets here, I mean, it's obviously not sentient, but it's going to choose to go the path of least resistance. And so if this RP is a lower impedance path, more of the current is going to go across it. If this is the lower impedance path, more current is going to go across it. That said, so basically, on this plot, in this middle region, that's where there's current going across both of these, and where this capacitance has an impedance that is on an order of magnitude or on scale with the total impedance we have in the system. So what happens when we get to really high frequencies out here, all we see is RU. And the reason for that is all of the current is going across the double layer capacitance, and it is contributing. But the thing is that at very high frequencies, that the impedance of that capacitor is so low, we just can't measure it. It's much, much, much lower than the impedance of RU. So if we didn't have this resistor and this resistor here, we would see this would continue down to lower and lower and lower impedances. This would would actually be at 90 degrees deflected the whole time. And so what would happen is when we got up to these higher frequencies, we might be down at, a micro-ohm or a nano-ohm or smaller. So the impedance of this, it doesn't go away, but it gets, once it once it gets a lot smaller than this RU value here, it doesn't measure anymore, because if you add 1 plus 1 times 10 to the minus 6, you get 1. That 10 to the minus 6 is that's not even within the noise of that type of system. And the same thing is happening at high impedance in a slightly different fashion. So, or I'm sorry, at low frequencies at high impedance. So at low frequencies, there will still be 1 or 2. I mean, there's a lot of current that goes through here, right? An amp is a lot of current. A milliamp, a microamp is actually a lot of individual electrons going through there. So yeah, there's a few of them are going to lay out and pop across this double layer, or be used to align the double layer at some. But what happens is almost all the current is going through here. And so even though this impedance is now very, very, very large, its effect on this, and this is if you the circuit theory, if you add, it's 1 over the impedance plus 1 over the impedance. So what happens is if you have an incredibly large impedance here and a much smaller impedance here, and you put them in parallel with each other, this one becomes inconsequential. And so that's what's happened here. Once you get up to these lower frequencies, and you can see that the phase is affected because this is a log plot. You can see that this seems to come up and level off before the phase, but that's because it's log on the modulus side. So the capacitance is still contributing factor up until it lays out to the 0 degrees phase. And what's just happening here is the actual impedance of that capacitor is very, very, very high. But since very little to no current is going through the capacitor, we're not measuring it. All the current that at those low frequencies, the bulk of the current that hits that junction travels across the electrode interface through this polarization resistance instead. And so that's what we end up measuring.
Okay, thank you. We have some more questions, but first, just in general, we will be providing a recording of this talk on YouTube, and we can provide, we can send everybody an email afterwards with a link to that recording. So if you have to leave now after the hour and you want to see more of the questions, then you'll get that follow-up link. So on to our next question or questions is, what is the reason of having noise at low frequencies, say between 100 millihertz and 10 millihertz? And can we remove the data for that range? Essentially, can we trust the data at the high frequency more than we can at the low frequency? And then the second part to that question is, what is the physical concept of inductance at low frequency?
Okay. All right. So let's deal with the first part first. Noise at low frequencies can come about for several different reasons. One of them is this open lead. So if you're measuring something that's incredibly high impedance, you can see noise just because you're at signal to noise limit for the system when you're trying to measure picoamps or femtoamps worth of AC current. You're going to have noise there, even if you're inside of a Faraday cage, which this case is. But more commonly, low frequency noise is due to changes that we see. So a lot of this comes back to this bad KK. So what happens when you get down to low frequency, there's a few things. One is you're a lot more likely to have a nonlinear response if your signal is too large. And that nonlinear response can look like noise because the way that it patterns around, it may average out to slightly different to slightly different impedance values. And so and especially if you're looking at the Lissajous. So if the Lissajous is getting more and more and more like it's getting if it looks like the signal to noise is getting better and better and better, then you probably are still linear. But if it stays bad for the entire time, nonlinear response can look like noise. If you have background drift, that does not generally look as much like noise. But if you have a non-causal system, and so I didn't talk too much about it because it's not as easy to deal with. So nonlinear can look like noise. Instability usually does not, but might. A non-causal system, a very good example for that would be pitting. If you're doing corrosion, and what happens with a pit is all of a sudden there's a penetration, a breakthrough in this oxide film, and the impedance drops because the corrosion takes off. So the current gets a lot larger, the impedance gets a lot lower. And so if you take a measurement when a pit has opened, you're going to see a lower impedance value. But then those pits have a tendency to seal themselves back off and they close. And once it's closed, the impedance jumps back up. And so if you have pitting corrosion happening and you're doing this on a corroding sample, then that a lot of times looks like noise at low frequencies. And that's an example of a causal, of a data that is not causal. So tripping up against these criteria for valid EIS can make data look noisy, even if the system is well within its ability to make those measurements. That last bit of the question, the inductance at low frequencies. I don't have a slide, so I'll just show you the inductor thing again here. So inductance at high frequencies is almost always cabling related, and it tends to happen with low impedance samples. At low frequencies, and now I'm going to talk about actual inductance, not bizarre system effects that are not KK transformable, but real inductance that you get at low frequencies is an effect of adsorption. And it's not truly inductive, but it models but it's actually a negative capacitance. What happens is when you have species that adsorb onto the surface of the electrode, when they desorb, they change the capacitance of that electrode. So when they're adsorbing and desorbing, and you see this at low frequencies, is when they get driven off, all of a sudden the capacitance jumps up, and that looks like a negative shift, and that models like an inductor at low frequencies. So it's an adsorption effect when it is real. It's not very common to see it. It's a lot more likely to see invalid data that looks like inductance than at low frequencies. But if you have samples where you know they have things that adsorb to the surface, sensors, biosensors, for example, if you've got any thiol containing thing with a gold electrode, stuff that you do know adsorbs and can come off the electrode at certain polarization or at certain voltages, potentials, then you can have that inductance at low frequency.
Okay. Thank you. I'd like to sort of go back to the first part of that question, because we had a related question since you were mentioning pitting and corrosion. And this is, somebody asked, why sometimes can't we get a good fit for models to use in inhibitor corrosion studies?
Inhibitors can be there. So inhibitors work in different ways. There are different classes of inhibitors, and knowing which one you're working with makes a difference, right? So some inhibitors are going to inhibit the anodic reaction, others the cathodic reaction, and others are just basically like almost like coatings themselves. They are laying themselves down in their providing a barrier to active areas on the electrode surface to things that are out there that would otherwise stick to them and cause corrosion. So it really depends on what type of inhibitor you have and the nature of that inhibition and what potential you're measuring at. You tend to do EIS around the open circuit potential for corrosion experiments. Actually, for most EIS experiments are done around the open circuit. So you've got the cathodic is inhibiting half of that, but not the other half. The anodic is doing the same thing, and so it shifts the open circuit potential. So if you're making a measurement of EIS and you're monitoring the EIS and then you add an inhibitor, you actually shift the open circuit potential. So there's a lot of things that happen. So that in an inhibited a corrosion system with an inhibitor getting added is a very complex environment. Monitoring the open circuit while make sure that you're measuring open circuit in between additions and watching how things are shifting, and make sure that that open circuit has stabilized before you start doing your impedance measurement if you're doing inhibitor analysis.
Okay, thank you. We have another question. It relates more to modeling. If we replace a constant phase element in a model by a capacitor, how can we make the model fit the data? It seems to be a very general question.
At some level, you probably can't. I mean, the constant phase element exists for a reason. Real systems are not purely capacitive. I coming back to this diagram here, I didn't talk about this, but this double layer capacitance that we see here, that is going to be the one that you get a constant phase element substituted for. This capacitance is right. The equation for a capacitor, you've got the dielectric of the solvent dielectric in between, but the other important element is this distance, how far it is between the surface, between your two charged plates. And in the case of a metal electrode and electrolyte, this distance is less than a nanometer. It's on the order of 3 to 4 angstroms. It varies a little bit with nature of the electrolyte and ionic strength and things like that, but it's on the order of, it's definitely less than 1 nanometer. When you polish your electrode, if your surface roughness is less than 1 nanometer, I would be astounded, right? Most of the polishing pastes, they cut off at, maybe 100 or so nanometers. I think you can get some alumina slurries that are down in the 10 to 50 nanometer range. But those polishing slurries, I mean, you end up with surface roughness that's on the order, if you're really, really, really lucky, single digit to maybe, like 8 to probably 30 or 40, 50 nanometers. 50 nanometers on top of a double layer capacitance that's based on the angstrom is like a mountain range. And so that is that capacitance is going to be very different across that type of a surface, and it doesn't end up being 90 degrees. And if you really want to see a 90-degree type double layer capacitance, go find somebody that's got an old mercury dropping electrode, because mercury is about atomically, as close as you can get to atomically smooth at that surface, and that's about as flat as you're going to get. That's as close you're going to get as to a perfect double layer capacitance. Coatings get there, but they get there the other way. Instead of having dealing with this roughness, they push this boundary way away from the surface, right? So if you've got a 1 micron thick coating, that's a pretty thin coating, but it's 1,000 times further distant relative to a double layer capacitance. So if you've got a model that fits very nicely with a constant phase element and you substitute in a capacitor, it's just not going to fit as well. You're going to get a capacitance value from it, but if you look at it on the Nyquist plot, this is what your capacitor looks like. A constant phase element is going to be a lot shorter than that. So basically, your data is going to be down here and your fit is going to be up there, and it's going to try and wiggle that model to fit. And it's not a good thing to do, because in order to get that to the way that the fitting routines work, a lot of times when you've got a big discrepancy between your phase, between a constant phase element and a capacitor, one of the things that it can do is it can mess up where these resistors are, and that you do not want to happen. So if you substitute in a capacitor, not only is it not going to fit as well here, but it's also probably not going to fit as well on these for the resistors, for RU and RP. Those values will not fit as well either.
Okay, thank you. We have another two-part question here. Is how does the working electrode geometry matter, and should we take any precautions to get accurate measurements on a cylindrical electrode?
It depends on the frequencies you're going to, and it depends on the dimensions of your cylinder. For most cylindrical samples, for like corrosion where you're in the 5 square centimeter range, or cylinders that are millimeters in diameter, versus impedance spectra that are going down into the millihertz range, you're not going to see a difference. Because what's happening is the radial diffusion component kicks in at way too low of a frequency. You're going to have other mass transport effects that screw it up, and you're not going to be able to measure. I mean, you don't make those types of measurements with electrodes that size. If, on the other hand, you are measuring with micron dimension cylinders, carbon fibers, carbon fiber microelectrodes in a cylinder geometry, you do have a radial diffusion component that plays into it. It does not affect things like the double layer capacitance, or because that is still, right, that double layer capacitance is still angstroms. So unless you end up with like a single atom thick layer, a single atom diameter cylinder, you're not going to have capacitive effects from having a cylinder, but you will affect your double layer. And so the biggest effect is probably, and this is that this Warburg diffusion element, if you go to low enough frequencies for a microelectrode cylinder, is going to change from an open version to a porous bounded version. And that's for people that do microelectrode work. That porous bounded is that limiting basically the diffusion, the radial diffusion component at a certain point, at a certain distance, it gets replenished, and so there is a steady state current that you get from microelectrodes, and that's reflected by a porous bounded Warburg.
Okay, let me see here. We have a lot of questions here, so I'm just asking everybody to have some patience as we work through them. We had another question, and this is probably relevant to everybody. Are there any special precautions to consider to prevent equipment damage while operating or while obtaining EIS spectra?
That is case by case. The easiest example to say yes to is if you're dealing with making measurements on powered systems, fuel cells, batteries, things like that. And the caution is where is ground in the system. So basically, you can accidentally short a battery or a fuel cell or any other electrode through the potentiostat. It's just that most electrodes aren't capable of generating their own power. They don't drive the system. So if you're measuring conventional, whether it's a sensor or corrosion or small batteries like coin cells, there's not enough power in there to really concern yourself with it. But if you are measuring larger batteries, fully charged, kilofarad plus supercapacitors, fuel cells, maybe electrolyzers, depending on exactly what you're doing, or if you're using measuring in parallel with an electronic load or power supply, which you can do because our potentiostats are all floating, you can actually make those measurements. If you short between the terminals, and there's ways to do that accidentally, I don't necessarily mean dropping a wrench between two terminals to short across them. So the easiest way in terms of our systems is knowing where ground is. And for us, ground is on the working side of the potentiostat internally. It's a virtual ground if you're floating, it's earth ground if you're not, but it's on the working side. And there is a black ground lead. So if you have the working sense electrodes connected to your working electrode on a powered system, and you have your counter and your reference on the generally negative terminal of that system, and if you have your black lead comes into contact with that counter electrode, then that will basically, because that black lead is at about the same point energetically as the working lead, that effectively shorts the battery through the system. That will cause damage. If you're working with powered systems in general, you want to take care not to short things through it most of the time. So that's one of the reasons that black lead on our systems, you remove that, the alligator clip, and it's a pin that can't accidentally short on anything. It's not a pin, it's a pin jack, and that way it won't accidentally short. So if you're working with systems like that. For the vast majority of users, otherwise, if you're not connecting to a powered system, you don't have to worry about any connection in terms of damage to the potentiostat. If you're connecting to a very high impedance system and you're not careful about things like open circuit potential and whether or not you've got a reference in there or reference lead connected, you can cause damage to a cell. So our potentiostats are all 4 terminal devices. That is, there are 2 leads for voltage sensing and 2 leads for current carrying. And all 4 of those need to be connected. For most 3 electrode systems, the blue and the green are work, sense, and working. They are shorted together, connected to working electrode. The red lead is connected to the counter electrode. That completes the current path. And then the white lead needs to be connected to a reference electrode that is in that same solution. If the white lead is connected to a reference electrode that you forget to put into the same electrolyte, or if it's left hanging, or basically not connected at all, then there's no voltage sensing. And so when you try to run a measurement, it keeps measuring that nothing's changing, and it's going to drive more and more and more current through it. So for some systems, for some electrodes, that might be problematic. So you need to have all of your leads connected, but that's not going to damage the potentiostat. Yeah.
Okay. Somebody would like to visit or ask about inductance at high frequency. When you see inductance at high frequency, is it simply bad, or could there be something meaningful there, such as if you ran a KK on it, is that meaningful?
KK is almost always going to line up pretty nicely on top of an inductor, on top of this inductive region. So basically, inductors are actual circuit elements. They are linear, stable, causal. So if you do KK here, it will come out perfectly fine. Whether or not is of meaning, that's what this shorted lead curve is kind of there to tell you. And there is a more involved EIS on low impedance batteries and fuel cells type thing talk that really gets into this. But if you are measuring a low impedance system that has inductance at high frequencies, you actually want to measure not a shorted lead, but a surrogate, a low Z surrogate. And that's because the shorted lead is going to have a different cable configuration. And so the inductance that you measure from a shorted lead is not going to be the same as the cable inductance that you measure when you're actually connected to your cell. So you need to generate a low Z surrogate. I think that's going further into details beyond the scope of this. We do have some app notes on the subject, and it'll be something to discuss in maybe in another version of this.
Okay. Let's see, how are we doing? We're getting close to about 12:30, and we're starting to lose participants, but we could probably take a few more questions. I have one here. This is dealing with CPEs again. Is how do we obtain capacitance in farads instead of the current units which we put out there, which are what, Siemens seconds raised to the alpha parameter?
There are 2 different equations that convert constant phase element values into capacitance. They give you slightly different answers, and the one that you choose requires you understand the nature of the discrepancy. So you need to know exactly why it's a CPE instead of a capacitor. And then you can use the appropriate response. We have there are calculations within Analyst that'll do it for you. We've got an application note that covers it. In general, I know that people submit and they're told by a lot of times submitting publications, responses you get back is you need to convert this into a capacitance. That's actually generally bad practice, because the constant phase element values are correct. It gives you an alpha, it gives you the Y value for the constant phase element, and those are correct. The second that you convert that into a capacitance number, you have made some assumptions. And if you're very confident in those assumptions, that's great. But the constant phase element values are actually better representative of your data than a conversion to a capacitance would be. Now, that doesn't change the fact that a lot of times people will write up a paper, they'll put the CPE values in there and they'll submit it, and one of the reviewers will come back and say, you need to convert that to a capacitance. That's doesn't, and sometimes you have to do it anyway. But there are a couple different conversion calculations that can do, and you need to have a better understanding of the nature of the discrepancy to pick the correct one, unfortunately. But you can do it.
Okay, all right, thank you. We have another one, which, and this is probably valid for a lot of people. If our open circuit potential is decaying or moving, should we switch to galvanostatic EIS for the measurement?
Maybe. So galvanostatic EIS versus potentiostatic. Nominally, you get the same data from both of them. The idea is that it's current and voltage. You're just applying one and measuring the other, and the ratio should be the same no matter which way you go. In practice, however, potentiostatic measurements tend to be quote unquote safer. That is to say, you don't worry about over-polarizing the cell. Applying a potential that gives you too much current back is not doing damage, because in that case you're dealing with a low impedance cell and it can handle the high current. However, applying a current that gives you too much voltage back it does two things. One is it drives you to nonlinear response, and the other one is it can potentially, depending on the electrode and things like that, cause damage to the electrode itself, whether that's accelerating corrosion too far, tearing off surface bound species, or for things like microelectrodes, can actually etch them away. So potentiostatic EIS is safer. Galvanostatic is mostly used when you need to measure very, very, very low impedances, where if you apply a 1 millivolt signal, you're going to get more current than the system can provide. So that's the one side of things. The other is where your 0 point is. So for a galvanostatic EIS experiment, your DC background is 0 current. So if you have system drift, it does drift. The voltage in your background is changing versus time in that case. If, on the other hand, you have a potentiostatic measurement, if you're doing potentiostatic EIS, your DC background is voltage. And so you measure your open circuit, and in that case, your DC background stays at the exact same potential throughout. And if there is any drift in the sample, you actually see it in your DC current changing over time. I don't know that I can tell you what the best response for you is. If having excess current flowing through there is a problem, then galvanostatic may be the better solution for you. If that voltage change is causing your impedance to mostly be unstable and give invalid data, then maybe anchoring it to a single potential, then relaxing and watching what the open circuit does. Ideally, you want to sit at open circuit and make sure that everything has come and stabilized nicely for you before you begin your measurement, but that's not always possible, I realize.
Okay. So we have another question here in chat, but I'm going to go ahead and jump on this one. The question is, how do we evaluate the performance of a coating with the Bode and the Nyquist plot, and what are the most critical parameters? I would, a bigger picture, this is more of a, we will likely have some more advanced EIS webinars where we can get into coatings in more detail. Jacob, if you have a quick example where you could show something, otherwise, that's probably a good topic in and of itself, dealing with coatings using EIS.
Nothing readily available for that.
Yeah. Okay.
Yeah, that's good.
Okay. So, so those are those are pretty much the questions in chat. There's a few here which are very, dealing with not so much the content that was covered today. So I have a copy of the chat and I can answer those individually afterwards. If people would like to submit questions, they could email you directly afterwards. We still have a number of people here. If anybody wants to raise their hand, if they would like to ask their question verbally, we could do that also. I can unmute you and we can allow that. Just click the raise your hand button in the chat. I believe it's probably under more, and we can see if you have questions. And if not, oh, here we go. Okay, please go ahead and ask your question.
Yeah, thank you for all the content. It's really wonderful. I'm trying to learn this EIS method for a coating steel or just for stainless steel, just as a practice. Once the data is done, I'm not sure which method to apply. I looked at the literature to develop a small model, but there are simplex method, KK method. So is there a specific recommendation? If you have covered, I kind of didn't catch it.
Not a specific recommendation, unfortunately. No, there's a lot. Coatings is one of the bigger uses for EIS, and the reason is because EIS is very sensitive to capacitance changes. And so with coatings, you get water uptake that causes a shift in the capacitance. There's a quick check, or REAP, Rapid Electrochemical Assessment of Paints, which combines EIS and looks at water uptake and combines that with the cathodic disbonding to get an estimated time to failure. But those are, I mean, there are limitations to how that can be applied. A lot of coatings analysis just looks at actually, you use that constant phase element and you look at the alpha value for that. And that alpha value is used for an indicator of coating quality for some coating types. Ray Taylor runs an EIS course every year. It's tentatively scheduled for fall of this year, and both he and one of the other instructors for that, Martin Kendig, have done quite a bit of work. Martin's actually the guy that published the paper on the REAP, and there's a lot of EIS of coatings information out there. There's a lot of different ways to do it. It's when that course gets lined up, I would strongly recommend taking it, possibly talking to them independently as well. But yeah.
Okay. Are there other questions that people would like to ask? Again, just raise your hand and we could unmute you and you could ask it. We'll wait a few more seconds. In the meantime, I just want to remind everybody again that we will provide a recording for this. We'll post it to YouTube, or for those who might be behind firewall that blocks YouTube, we also do have Vimeo capabilities, and so we can get these videos to you in some way, shape, or form. We also have a copy of the chat, so if we did miss anything that was asked, we can follow up in general and one-on-one with you. And of course, please feel free to submit questions, email us, or submit through our website through the tech support form if you have questions. We're definitely more than happy to help. So at this time, I think we're going to wrap it up, and we're going to say thank you for participating, and we look forward to doing more of these in the future for you. So everybody stay safe, stay healthy, and we look forward to seeing you again soon. All right.
Thank you very much. Take care.
Thank you.